No, this is... Okay, so welcome to the third and apparently last lecture in this mini series of, I have to say, recycling talks, and we go a little bit backward in time. So all the previous two lectures were actually later lectures. So this is a recycling lecture, and it may be a little bit older style. Yeah, also with the PowerPoints. Yeah, but I hope this doesn't disturb anybody. And we'll have a little bit of repetition also today, but maybe that's not such a bad thing. What we are going to do is to look at the optimal relaxation parameters specifically for the Cumulant lattice Boltzmann method for solving the Navier-Stokes equation using things that we more or less learned in the last two lectures. Yeah, I recognize there would be also another topic that we could touch, but this is still now outside of this lecture. I'm thinking about maybe doing a fourth lecture on, but this must be somehow outside of this, because there is two different aspects with trying to get lattice Boltzmann to higher order accuracy, and one here is related to how we treat diffusion, yeah, and this is what we are talking about today. And then there's also the advection part, and what we have discovered here is that there is surprisingly a relatively simple solution to improve diffusion, but it is more complicated to improve the advection part. So there's also possibilities, but we recognize that even though we worked on them, they have not become any mainstream now. Whereas this improved diffusion thing is actually widely used nowadays. When it comes to high Reynolds number flow simulations, because unfortunately the entire thing is, I don't know whether unfortunately or fortunately, but we can achieve these optimal relaxation rates in the limit of vanishing viscosities. Yeah. So unfortunately, if you deal with flows with very high viscosities or very, very low Reynolds numbers, so that wouldn't work for you, and we'll later see why this is the case. Okay, so there is a little bit of agenda to get our heads again on lattice Boltzmann, because we have not talked about lattice Boltzmann for the last 2 weeks. And then we go through the steps that we have to do to get to these optimal relaxation rates, and also show a little bit how we then tested this. So now we start with all of our repetition. Yeah, so we have the lattice Boltzmann equation. We have the post-collision state and the pre-collision state, and we shift this by half a time step. And then we have this characteristic diagram that I've used in all the previous two lectures and also in the full lecture in lattice Boltzmann. So, and by the way, if anybody is listening to this on the internet, on the channel, we also have the full lecture with 14 lectures on lattice Boltzmann. Yeah, there you can go. So, and we specifically focus on the lattice D3Q27. Also, this is where everything here is derived for. Okay. Yes. So there is that's kind of a little bit controversial. What I'm talking here, because the big shots in Lattice Boltzmann always question this here. This is why later years I also took this a little bit outside of my presentations. So you could think about what is going on in a fluid in fluid and having binary collisions and multi-body collisions. Yeah. So, and if you have any idea, any knowledge on the Boltzmann equation, then of course you know that the Boltzmann equation strictly focuses on binary collisions and not multi-body collisions. Yeah. If you are on this lattice and you split up all the discrete operations that you could do, then you see that binary collisions are not enough. Yeah. So these things here. Okay. So this is a particle. The particle going in like this and going out this way. Yeah. Or doing this 45 degrees. Turned around. Yeah. This is not enough. So when I started with Lattice Boltzmann, we were trying to do an integer lattice guard. I'm so old. I started with lattice guards. Yeah. And there, the question is, what are the discrete operations that we do on our populations to change the field? Now you see that, okay, so these operations here, they will basically change the second order moments. Yeah, and these operations here that are displayed here, they will change the third order moments. Yeah, so a third order moment change. Now I'm saying something very controversial. Yeah, if you later cite me, yeah, then so the binary collisions change second order moments. Three particle collisions change third order moments. Yeah. So of course the third order, fourth order, and so on, they are not conserved in the real Boltzmann equation. Yeah. Yeah. But the Boltzmann equation actually, the Boltzmann equation. Okay, so a little bit what is the physical idea? And this is where the things get a little bit fuzzy. Yeah. So you have basically you don't have three particle collisions because they would be too unlikely. Yeah, in a dilute gas. But what will finally happen is that if two particles have interacted and another two particles have interacted, they that's not what I wanted to say. So there's these two particles interacted and then they go off, and one is interacting with this, and then the other one is interacting with the same one later. Yeah, so it would not. I mean, this is not really a binary collision, because there isn't the path of this particle is influenced from this particle when it hits this. Otherwise, it would not hit. Yeah. So then after some time, yeah, there is this correlation which actually Boltzmann explicitly excluded from his statement. Yeah. So, but in reality, I mean, but also for Boltzmann, this would be controversial. Yeah, because what he is actually claiming that what the idea is actually claiming, of course, this is not what he thought that would happen. Yeah, but this model. Yeah, so that a particle will know. I mean, it's completely uncorrelated it will never again meet any other particle. So it will never be influenced by itself later. Yeah, which of course doesn't. I mean, then in principle all the particles would be completely disjoint. Yeah. So, and this is not true. So actually these things happen. Yeah. So, but just they happen. They don't happen directly. They happen by particles having some history and then meeting again. Yeah. And this of course is a completely less common than these binary collisions. Mm-hmm. So these things would happen on a different time scale in principle. Yeah. But all of this is in the sense of this is kind of averaged out in our usual models. And the usual model, of course, is the BGK model, because it simplifies everything so much. Yeah. So okay, in the exam you are of course potentially asked what the BGK model is. So BGK model is this complete simplification down to one interaction time. So this is basically, you have this omega, even though there is this Heon correction, which let's talk a little bit later. So, but otherwise this omega is a frequency, that's the inverse of the mean-free time. Yeah. And what we do here, this includes these kind of higher order collision, because the particle kinds of collides with an equilibrium. So it collides with not with another particle, but with a bars that is the integral over all the particles, if you will. Yeah. So that's a big simplification. And okay, so this is already discretized. So let us we use this discretized in lattice BGK. So this is one of the possibilities that we have, and then we have regularization. So regularization comes in different formats. So nowadays people talk about recursive regularization, and then there's also hybrid recursive regularization. So this is methods that are used by the Marseille group, for example. Yeah, what is this labs? They have them. Okay, so I kind of, now I'm online. Okay, it's used in France. It has a little bit history with the French automotive industry. There's where it's where these things originate from, and they are in a sense similar to central moments. So they are using Hermite polynomials and reconstruct the higher order moments from the lower order moments. So that's something very, very roughly. So they have similarities with central moments and cumulants. Yeah. So orthogonalized central moments, if you will. Weighted orthogonalized, that's important. Weighted orthogonalized. But they remove the higher order moments. Yeah. So this is basically what we mean by regularization. Because there are several ways, there have been several methods that have been called regularized methods, and what they have in common is that they remove, or they attempt to remove, maybe sometimes, the contributions of the higher order moments, and this is usually done by, the higher order moments, they are there. Yeah, so actually you cannot absolutely remove them, but you can remove them from a post-collision state. Yeah, so you can always remove them from the post-collision state. It's difficult to remove them from the pre-collision state, even though you could do this, but then you would have to solve an implicit equation, yeah, because usually what is the pre-collision state is what's coming in, yeah. So you could reformulate this such that it is implicit, and then you could remove, by solving the equation, you could remove the pre-collision non-equilibrium higher order moments, but then you would have them in the post-collision, yeah. Or you could try to make this symmetric. I don't know. So anyway, so this is the idea is just take them out of the equation. Yeah. And no, I mean this is the idea, but this is not completely successful, I would say. Yeah. So, and then the other way is to have multiple relaxation time. Yeah. Which is here stated in the classical way by a transformation matrix into moment space, and then you have this S vector. So this is the, I think it's actually diagonal matrix. Okay, not my format. So there in this there is the relaxation rates for the different moments, and you give them different relaxation rates. So originally, as we know, the M is fixed, so static, yeah, and so this means, because M is static, it is raw moments, not central moments. So you can't make M as a function of velocity, then you can make it a central moment, and then you can choose different ways of orthogonalization. So you can have unweighted orthogonalization, as is classical the case, or you can also have the weighted orthogonalization, which is, also classical. For example, if you look at work from Della, yeah, so they always used weighted orthogonalization also back in the 20 plus years ago. Okay, so all of these things can be widely criticized for having different problems. Yeah. So this thing here is mostly unstable. Yeah. This thing here can be very dissipative and okay, so usually the regularization method is very stable. Yeah. So this is good for industry. They love it. They always give me a result. Multiple relaxation time method. Well, so in principle, you could always say that these two things are basically included in here. Yeah, because you just choose your relaxation rate. So you can just choose the relaxation rate so that it either becomes VGK or that it becomes regularized methods, provided that you use the right matrix and the right orthogonalization to the matrix and so on. Yeah, so that's the caveat here. But otherwise you can always use MRT, and this is the most general. Yeah, but then the question is, so how do you parameterize this? And this is also something that's okay. So there are two schools of thought. Yeah, the ones who say, Okay, so this is this. So general, we basically have solved all our problems with this. And the others say, well, you know, you didn't tell us what S is. Yeah? So the one says, okay, so then I tried this, I get a bad result. Then the other guy says, okay, do you have the wrong S? So then he says, so what is the right S? Yeah? Well, you have to try out. Yeah? Okay, so you see how these things work. Now, the thing is, so we want to have a good S, yeah, but then, so we would like to optimize S, but in order to optimize something, we need an objective, yeah. So and the objective is not so clear, and there may be different objectives, yeah. So, for example, one objective that is often used is you want to have it stable. Mm-hmm. Yeah. So and then we know what is stable. Regularization is stable. Yeah. So we choose S such that it ends up in regularization. Okay, let's have a look in our. Okay, we have spent 25 minutes doing nothing. Now comes the teaser. Okay, so yeah, let's look at an example that we used for paper, and this is the Taylor-Green vortex. So there are several Taylor-Green vortices. One is in 2D and one is in 3 dimensions, and here we of course use the one in 3 dimensions. Yeah. So this is basically here what you see here is so there's a u and v, and okay, so there's no starting velocity in the z direction, and there is, for reasons to do with the centrifugal force, there is of course also some pressure distribution here. Yeah, so it's basically a sine wave. It's in a periodic box, and there is a little bit a strange definition of the Reynolds number, because the domain is not of length L, but it's of 2 pi L. But the Reynolds number, I mean, this is a standard benchmark, so I cannot change it. Yeah, so the Reynolds number is built on L. So even though the domain size is 2 pi L. So the actual Reynolds number, in my opinion, would be a little bit different, but okay, because it's not according to the wavelengths. Yeah. So whatever. So now we look at this with 9 different simulations. So why 9 different simulations? We choose to have 3 different resolutions, and we choose to have 3 different Mach numbers. And the reason why we are doing this is because, as you have learned from another lecture here, because the Navier-Stokes equations have 2 independent smallness parameters, time and space, yeah, it is unclear how to scale them. And there are these 2 common ways of scaling them, and this is the acoustic scaling and the diffusive scaling. And now you can guarantee that whenever you use diffusive scaling, somebody would ask you, why don't you use acoustic scaling? This is for clear. The other way around is a little bit less clear, but would also happen if you use acoustic scaling. Why didn't you use diffusive scaling? Yeah. So okay. I mean, reminder: acoustic scaling is you scale the time proportional to the space, and diffusive scaling you scale the time proportional to the space squared. Now, if you do these 9 simulations like this, you have acoustic scaling in this direction. Yeah, 3 times. You do acoustic scaling 3 times, and you do once diffusive scaling here in the diagonal. Yeah. So now you have all the results, and now you can interpret them the way you like. Yeah, you can look at them in terms of acoustic scaling, and you can look at them in terms of diffusive scaling, because you have done both, okay? So now what is then happening? The thing is, this is an unstable, configuration. So you start with these vortices. So what we see here is Q criterion. Q criterion is, is here for displaying the course of a vortex. Yeah. So you see this is then decaying after some time, and it is how three-dimensional turbulence is actually working. Yeah, it decays to smaller and smaller and smaller vortices, and then when it has vortices, so it generates smaller and smaller vortices in this energy cascade, and once the turbulence is there, the energy will just dissipate in viscous way. And this is something that we are going to see here. So, what we are displaying here is entropy, and entropy in this sense is, so entropy is defined. Is defined here in this way, but I'm not discussing now a lot what entropy is. The entropy is in this, if we are in a periodic domain, so when there's no influx outflux, yeah, then entropy, yeah, entropy is equivalent to the time derivative of energy, yeah, of kinetic energy. The time so dissipation basically, yeah. So the time derivative of this is proportional to dissipation. So, and it actually so in principle, if you calculate it's not shown here, but in principle is when you calculate the kinetic energy in the system, yeah, and then take a time derivative of this, you should end up with the same plot, yeah, and this is in particular true if you resolve everything. If you don't resolve everything, so in practice, if you don't resolve everything, and this is the case here, that we don't resolve everything, because resolving everything requires 512, a resolution of 512. So that would resolve everything, and we would always get the right solution, no matter, almost no matter how we calculate it. Yeah. So okay, that's about that's about this entropy. Now look at these results. So here BGK. I know some people say that they never get the right result with MRT, for example, and BGK is actually the gold standard for this problem, even though there is, as we see, a problem here with BGK. So, okay, so the dotted line here is the benchmark solution that you get basically if you resolve this fine enough. And then, one thing is important. So if you resolve it fine enough, then every numerical method, maybe different numerical methods need different resolutions to be fine enough, but once you resolve it fine enough, so every numerical method will give you the same result. Otherwise, it's wrong. Okay, so there is no reason why any of these methods would not give us the right result once we resolve everything here. Yeah. So, but we are not resolving everything here. Yeah, we start with 64, 128 and have 256 resolution. Yeah. So, and now what we observe is that a BGK is unstable when there is not enough resolution. I mean, like with 64, then you see the energy is exploding. Yeah. So there's stable for some time, and then, I mean, no, you cannot be stable for some time. Yeah. It's by definition not possible. Yeah. Yeah. So if we have enough resolution in BGK, yeah, we'll, basically the entropy is increasing, and then, so this is where basically what is happening here so far. Energy is just redistributed. Yeah. But so entropy is biased towards smaller scales. Yeah. So energy is distributed from a large scale to small scales, and here when we are on the peak, this distribution, yeah. So here it starts that there is more dissipation than redistribution. Yeah, and so it will finally die out. So one thing, if we compare BGK to regularization, and the type of regularization that we use here is based on a cumulant regularization. Yeah, so this is the models that we call K15. When we compare this, there are two very important things that we, okay. So one important thing is regularization is always stable. Yeah. And even if we had, lesser resolution, it would still be stable. The reason why it is stable is because it is dissipative. Yeah. So you see that the redistribution of energy in BGK is much more, even for the low resolution, where this looks promising in the beginning. Yeah. So everything seems to redistribute things nicely. Yeah. So, and here in the regularization, what we observe is that there is not enough energy converted to, okay, so there is a caveat here also, because entropy is biased towards lower resolution. The resolutions that are not resolved cannot carry any energy. So it's completely natural that these things here are lower, because they are missing wave numbers. Yeah. Okay. So they need to be smaller. Yeah. But anyway, you see they can be much higher in BGK. So this is one thing that we observe, and then there is another important thing. So here, BGK, you see only 3 lines, even though here you see that this is a little bit different lines here, and this is to do with the difference between acoustic and diffusive scaling. So I told you we do everything with 3 different time steps, and in BGK is what you like to expect, that the time step actually doesn't matter. Yeah, so they always overlap each. So there's a small, here in instability you see a small difference, but otherwise they're completely on top of each other. If you use regularization, it becomes very obvious that different time steps do different things. Yeah, for the same resolution. And now you have a look at how this actually works, and this is something that your professor I mean, there's difference between practice and theory, right? So your professor tells you in the lecture, because he doesn't want to discuss everything to this, you make your time step smaller, you get a better result. So in BGK, it doesn't matter. And in regularization, it's the other way around. So because you see here, if you make the time step smaller, in all three cases, if you make the time step smaller, the dissipation becomes larger. Yeah. So, but this is in regularization. Yeah. So now we also have the optimized methods that maybe if I'm finally start talking, we'll come to this. And well, okay, so this one here, you see it has for the medium resolution, it has similar energy. It's for the higher resolution, it actually gets, I would say, much closer, like twice as close, I would say, something like this. And it still remains stable for the low resolution. And what is important here also is that even though there appears to be a little bit more dependency on the time step than in the BGK, it is substantially less than in regularization. So now finally coming to the objective as to how do we derive these relaxation rates here that optimize this methods. Okay, so there's anyway also energy spectrum, where you see in BGK there is some unclarity here. So I would say that, energy spectrum obviously gets a cutoff at the wave number of the resolution. And what you basically see here is that there's a lot of energy at higher wave numbers as the ones that we are actually actively resolving here. So actually, it's no wonder that something missing from the entropy. Okay, now comes the theory, and there is a bit of repetition, but also a little bit of simplification and doing things a little bit differently from what we learned in asymptotic analysis so far. So again, we have here the Lattice-Boltzmann equation, and then we have the pre-collision and the post-collision state, and then we rewrite the pre-collision and the post-collision state as an average state minus half a collision term, and a post-collision state in the average state plus half a collision term. And this brings us to this form of the Lattice-Boltzmann equation, where again we do this. We start with this half shift here. So recently somebody wrote to me that there is something confusing in this way of writing down the Lattice-Boltzmann equation, because even though we store the populations in between, the collisions don't happen at a half time step, they happen at the full time step. So then now you could argue, should these things here be not at the full time step? Well, the reason why we have them here is actually coming from this transformation. And we assume we do a Taylor expansion, so we kind of assuming continuity here. this is why they would be taken at the same time step. Also, if you the other thing, of course, is that if you said, so this here is at a half, so the population is at the half time step, and then the collision, the other half time step later, but it would also be the collision, this is an ambiguity, yeah, because it has the collision one half time step then later and one half time step before that, and you could do both. So now what you could argue is, because you can do both, you do the average and then you interpolate to this, which to second order would be the same as assuming it would happen at this in between stage, but not to higher order than that. Yeah. So actually, the question where the collision takes place and whether this should be used to refine the expansion is actually a good question. Yeah? And everybody is, of course, encouraged to make their own contribution to how to analyze things. So there are different ways of analyzing things. Lattice Boltzmann. Important point is there are still assumptions behind these, and the higher order you go with this, the more precise you need to be. So what we are doing here is apparently empirically accurate enough for what we are doing, to go into forced order. But of course, the higher you get with things, the more rigor you have to apply. Yeah. So, everybody is welcome to invent their own analysis method. Yeah. There's also analysis methods that are less. We also do some simplification here, because the problem is the very sophisticated analysis methods give you too much information. And so you have to actually always, the art of modeling is to reduce your information to exactly what you need. And this is what we also try to do today. Okay, so, this is not God-given, yeah? Right, so what we do is we put everything on one side of the equation, so that it becomes equal to 0, and then we take the Taylor expansion of both the populations and this collision term that in all spatial and temporal directions, which gives us a fourth dimensional Taylor expansion. And this omega here is, this is in terms of populations, and this here is also in terms of populations. Then we remind ourselves of the definition of the raw countable moments, and they are also in the average case. Yeah, and now we see that due to what the Taylor expansion does, there is this counting. So we count so there is these directions ijk. Yeah, so if we take moments of this equation, then we see there's also ijk here. Yeah. So, and what we then discover is that if moments of the expansion are taken, and the expansion is in a hierarchy of increasing orders of these moments. Yeah, and this is true for the m and then for the omega. Yeah. So, and I don't know what is coming for the, right. So, and now what we had in the last lecture is we can drag one of them out, yeah. So the zero order in the expansion out, so that we can rearrange it like this, so that just that all of the indices at the same time are zero is excluded. So we put this, then we have a recursive equation for the collision term. Yeah? Right, so there was one thing that I wanted to say and I've just escaped my memory. Yeah, right. So one important warning here, this thing works in raw moments. Yeah, so I often observe, okay, often now, we don't have that many students doing this, but you know, beginners in this think, okay, sometimes, I mean, I've observed this, why don't we use central moments here? Yeah. I mean, this is a question you could answer. Why don't, I mean, it looks like we could just plug central moments into this. By doing this in the frame of the moving fluid, why is this a problem? I mean, the thing is, it looks like it would simplify your equation so much, yeah, because you don't need to worry about a picture. You don't know. Well, because the velocity, I mean, because then you would do your expansion around the velocity at your expanding point. Yeah? But the definition of the moments would be different in all the other points of the domain. So when you use central raw moments, so the definition of the moments is the same everywhere. Mm-hmm. So you can do your Taylor expansion. Yeah? Mm-hmm. Otherwise this is, I mean, otherwise you don't have this, you cannot just plug this redefinition here, because here you would have velocity in the definition, yeah, and the velocity would not be the same in a different place. So in principle, of course, I mean, you can do this in principle. You could plug in here the definition of central moments, but then you don't get this equation. Yeah? Mm-hmm. Yeah, so you would get all the velocity terms, yeah, that are somehow in this. They will automatically appear here somehow. Mm-hmm. So you don't get this simple result. Yeah, so this is of course now a little problem. So, I mean, this biases you towards using raw moments because you're doing the analysis for raw moments, but you can still express the raw moments by central moments, for example. Yeah. So this is something we are not going to do today, and then coming to why in a minute. But first of all, now we go to again a little bit of repetitions for I believe, now we do the discretization, and what we have done so far was completely general and independent of the lattice. Yeah? Now we have a specific lattice with 27 velocities. And here these moments, yeah, so they have this aliasing property. If I hope you are familiar with by now, yeah. So which means because the velocities can either be -1, 0, or 1, yeah. So the indices here will just repeat. So M100 is the same as M300 and 5 and so on. Yeah. So there's only the difference between 0, odd, and even. Yeah. That's the only difference here, and the same is of course true for our collision terms here. Always write operator, which is not very accurate, it's the collision term. So now the collision term is not only in the recursive expansion itself, but it's also inside the definition of the moment, because the moments are always, this is the average moment, so it's the incoming moment plus half the collision term, and then each moment has a relaxation process and is basically built up of equilibrium minus the mean free time between these things to happen, which for binary collision with the mean free time between collisions, and for other collisions would be, their correlation time until they meet somebody again that they met, that their partner has met before, yeah, so that they influence each other. And this is of course here using the ion correction, yeah, which I don't want to spend a lot of time now here. So the tau is actually not, due to the discretization, it's not the inverse of the frequency, but the inverse of the frequency minus 1/2. So now BGK has only one of them, and the objective here is to use several of them. And now we'll very briefly talk about cumulants, where I also don't want to spend a lot of time with. Everything concerning cumulants is kind of confusing and controversial and so on. Yeah. So the basic idea behind cumulants is that instead of, okay, so what is the objective of using cumulants? Yeah, there is, when we divide our problems into its different moments, yeah, then there has always been the question, now how would we do this? Yeah, so we can simply use the countable moments, but there is some reasons why this is not a good idea, because we do not respect the isotropy of the system. So what was originally proposed by the French people from Lallemont and Deaumier, and of course also Lichilou and this entire group in the end of the last century that was there active, was to use physical quantity. So try to use a physical interpretation, heat flux and so on, and then they run out of ideas what these things actually mean. Yeah. So okay. And then there are different ways of orthogonalizing them, and so it's confusing. Yeah, it's confusing to say what how would we separate things? So the idea behind this MRT is that different quantities have different relaxation rates, right? So, and if you ask the question, so how would you divide your problem in different parts if you want to maximize the number of relaxation rates that you can apply? Then you would have to make sure that these things are in a sense independent of each other. And now the problem is the really definition, and this is what people have completely different opinions apparently, even though it sounds simple. Yeah, what is independence? Yeah, I mean this is apparently not only politically, yeah, but also mathematically not. I mean, I guess it's well defined, but not among these people who are using Lattice Boltzmann, because this is, they are not. We are not. The Lattice Boltzmann people are not fine mechanics. They are not very rigorous in their mathematics usually. Yeah, me included, of course. Yeah, but there is. So there's no very good definition of independence, and the cumulant is has a little bit the idea is when we want to have the idea is if we want to attach different relaxation rates to different things, so they have to be independent. And now our definition of independence is that these quantities should be independent, should be independent random variables. Yeah. So they would be so if they are independent random variables, so we turn the argument around, which we are not completely sure we are allowed to. Yeah. But let's just do it. If these things are independent variables, then their joint probability distribution would be the factor of the probability distributions of these individual quantities. Yeah? So, and this is what we use as the definition. So we assume that that we can factor out, yeah, these distributions. And okay, I'm getting messages. And then we take the logarithm on, so we take the logarithm on, of course, the moment generating function. Yeah, so the moment generating function is either the Laplace or the Fourier transform of this, and then we take the logarithm of this and make our series expansion of the logarithm, so that we turn this product into a sum. Yeah. So now none of this is proven that this is correct. Yeah. So that's just the basic idea behind this. Yeah. To separate stuff. Yeah. And then this also doesn't solve all the problems, because, for example, what is not included in this idea is isotropy. Yeah. So you have to care about isotropy in a separate way. Again. Yeah. Because now, X and Y, they are now simply independent. You can put them to different values, which you should not, because you know that the space is independent. So now, yes. So talking about isotropy, yeah. So there is different ways how you can order the things. So basically, okay. So what we do is we now relax the cumulants, yeah. But here we also have to separate things out. So first of all, there are things that are conserved, yeah. So we don't talk about these, yeah. So there's this, so there's some mass in principle, and there's the momentum things. By the way, these cumulants that we are using here is cumulants scaled by density, yeah, just for simplicity, because the real cumulants always, you can only compute actual cumulants only for populations that are normalized to 1, yeah? Which in Lattice Boltzmann is not the case. So then there is the second order things that due to isotropy has to be recombined in this way, and then there is energy stuff, and here I have a few green things introduced here. So these things here are correction terms that are used to eliminate some errors from the advection. Yeah, and this is related to what I was talking to in the beginning, that there's also problems with advection that is related to the way things are discretized here. So I don't want to talk about this today. So this is a compensation for discretization errors that is due to the finite number of speeds. So then also the third order moments for cumulants for reasons of isotropy have to be rearranged in this way, yeah, so that we take the sum of these two cumulants and the difference between these two cumulants, yeah. So this is very important, because then, I mean, we basically have 6 permutations of these cumulants, but we rearrange them in their difference and their sum in that way that we have that we can attach 2 different rates, because it is not possible to, by any rotation, to turn this into this, yeah. So they are separated variables, yeah. Interestingly, there is, in a continuous space, there is a rotation that would turn this here into this here. But on a discrete space, this is not the case. So because we are on a discrete space, we attach a different relaxation rate here, which, again, as I'm saying, that this is due to the shortcomings of our discretizations. So physically, this should not be the case, and I'm on record in claiming in my PhD thesis that these guys here should be the same from a physical point of view. So you see, I changed my mind, yeah, and from in a continuous space, velocity space, they would be the same. In a discrete space, they are not the same. Okay? So, and then there are first order moments, cumulants, and what I create out here is their fifth and sixth orders. And for the fifth and sixth orders, I write here omega h, and this is what I mean higher order. And the reality is that when I made this expansion, I was not able to make the expansion to actually see what is the influence on this thing. maybe computers have improved now and we could try it again. And the thing is, the expansion, I mean, if you is growing in complexity, it is growing exponentially in the order. That's one thing. And the other thing is, of course, you could go back to this question that somebody asked, whether it is, whether we do everything correctly by putting, by putting the addition operator at a specific point in time. Yeah, because the further you go in your expansion, the more rigorous you have to be. Yeah, and so assumptions that were okay on one level could go out of scope. Yeah, and when you increase your order, somebody is completely getting on my nerves here. So, yeah, okay. So here, if you want to do some useful research, you can go on, do the expansion to this order, see whatever problem is you are running into, and I say it's not necessarily funny, yeah, and see what you can do here. So here these red things that I put here, they have an important history. I should wait. Do you have any time constraints? Okay, maybe then I can talk about history a little bit. Let me see what is coming next. Okay, no, I don't talk about. I talk about the history later. Yeah. So here I do something bad. I put, okay, so this is already, yeah, omega h is also in the fourth order. Yeah? Because I also don't know what exactly to do with the non-equilibrium part of the first order moments. But what cumulants. But what you see, I'm putting something in the equilibrium of the first order moments. And these things are some derivatives of u and v. Yeah? So I simply put them there. And I put some factor a and b, yeah, into this. So this is unknown parameters, a and b. So why is this bad? Cumulants, I mean, just cumulants that are not conserved should always have an equilibrium of 0, because what they describe is the divergence from the Boltzmann distribution. Yeah. So how much does things get out of equilibrium? So cumulants, their equilibrium should be 0. Mm-hmm. Now I explicitly put them not to 0. I mean, I should say I should say that in complete equilibrium, these derivatives that I put here, they would be 0. Yeah. So the actual equilibrium for the actual equilibrium in the sense of
steady state.
Not of steady state, in complete what is this, heat death, yeah, where everything is the same state, yeah, they would still be the same. They would still be 0, right? But as long as the rest is not in equilibrium, though, they are also not in equilibrium. Okay, this is basically due to, again, us being on a lattice and us having kind of, screwed things up due to discretization already. Okay? Let's briefly talk about these strange derivatives here. Where do they come from? So in hybrid recursive regularization, and these derivatives come, of course, from finite differences. Yeah, but some of them can be computed directly from the second order non-equilibrium central cumulants. Yeah, so the non-equilibrium cumulants of second order, they encode some of these derivatives. Not all, I mean, not all of them, but all of which we need. That's important. Yeah. So we can take this pre-collision populations, cumulants, and from this we can derive what is the derivative of u by x and v by y. Yeah, so these can be computed directly, and some of them can only be computed in sum. So one important thing is, because we can compute them only in sum and not in difference, we have no means to compute the vorticity. Yeah, because the vorticity would be the difference. Now, there could be somebody is commenting that no, there is a paper in the group of one who has shown that it is possible to also get I just said it, not rotate the vorticity. Yeah. What did I say? The vorticity, yes. So, okay, so in the group of one, they derived a way of computing the vorticity, but this was, they used a trick by putting, I mean, a similar trick to what I was doing here. They put something into higher order moments to make it anisotropic, so by using the anisotropy, they could somehow extract things. But, I mean, then they already used the anisotropy, so they cannot use it again. So you have to, if you do this, you cannot do the other, okay? Right. Okay, so we use these things. This is a little bit exotic. I don't want to go into this now. We derive these things from the second order moments, and then we put them back into second order moments to do some corrections, which is possible because there is a particular asymptotic relationship between them that allows us to do this. Yeah. Okay, it's not the topic of today. And then we put corrections in these first order moments. So this is what we had here, right? In these first order, and they are here for compensating for these missing terms, because we have only finite amount of cumulants. Yeah. And here we add this additional degrees of freedom A and B. And then we have omega 3, omega 4, and omega 5. These are the relaxation rates for the third order moments. Omega 1 and omega 2 are the relaxation rates for the second order moments, whereas omega 1 is the shear mode and omega 2 is the compression bulk viscosity mode. Yeah, so they are physical quantities. So they are given by the system. So, and omega H is something that would affect the next order. That is no longer the leading order error. Now I'm ready to tell my story about this, because finding a relaxation rate that would eliminate the leading order error. Yeah, so this came under the subject of magic parameters, and it comes from observation by Irina Ginsburg and also Junier and a few others. First paper, I think Ginsburg and Adler, I believe, back in the time when they were in Kaiserslautern. I mean, back in the 90s, so it's something like almost 30 years ago now. Yeah. So they could show that when they have the third order relaxation rates, or actually they distinguish only between odd and even relaxation rates. Yeah. So second order for viscosity and third order, which is then even order, yeah, for this compensation. So they put under certain circumstances the relaxation rates to a certain value, a certain relationship, and then they got, they could in some cases even got exact results. Yeah, so at least much better results than otherwise. And this came to be known as magic parameters. Somebody later, I think Dubois and came much later to Lattice Boltzmann. They didn't like this statement of magic parameters because he is a real mathematician, so he called this quadratic parameters because he got shows that there are certain combinations of these relaxation rates that would give you fourth order convergence. Yeah. So because this is what Lattice Boltzmann is the second order method, and super convergence would mean that there is some trick that you can play that would give you fourth order convergence. Now the question is this something you want to spend your life with? And in principle, you could say this has been known for a very, very long time, and it has not been picked up by many for 20 years, kind of. And you should usually think that if there is something simple, like you just put a certain parameter that you have anyway to a certain value, and this turns second order convergence to fourth order convergence, that everybody would jump on that, right? But this was not the case. Yeah, and the reason was that this is kind of regarded as chasing ghosts. The problem is that with these super parameters, yeah, so they could, for example, be derived for a certain case. Like you have a pipe, something very boring. You have a pipe flow, yeah, and the pipe is going straight, and then you have a certain parameter that gives you an exact result. Now, the pipe is not going straight, but it's going 45 degrees. You can also get exact result, but with a different parameter. Okay? So now, what is this good for? I mean, there are very simple examples where you get very high, very accurate results if you know the parameter that you put it. Yeah? So basically, and they are very simple. So now this is a parameter, there's a global parameter that you have to set in all of your domain. Yeah? So what happens if you have a pipe that is, if you have a slightly more difficult problem, where your pipe first goes this and then goes that. Yeah? Yeah? So, it's like, I think around the years after 2010-ish, it was kind of damaging your reputation if you would say that you're working on that problem. So now comes my my PhD student about, Andrea Pasquali, and playing around with these parameters and getting good results. And so he says, so in principle, we should, there should, why don't we work on that? And I said, so because it doesn't have a solution. And there was a good there was a theoretical reason why there is no solution. Yeah? Because, and we come to this in a moment, you can, from a theoretical point of view, you can easily determine how many error terms, independent error terms, you would generate with that the discretization would generate. Yeah. So and there would be just counting the diffusion terms. Okay, there would be 5 error terms. Yeah, that you can simply by isotropy arguments, you can determine that there would be 5 independent error terms. And you can also determine from scaling arguments that they will only be influenced by the relaxation rates of the third order cumulants. Yeah? And this is why it now became important that we have this split here, right? You see, we can split them in 3 different parts. So if we didn't put them in plus and minus, then all of them were the same. And then, as I said, this can be turned into this. So basically, we could say the third order moments, they should cumulants, they should all have, physically speaking, the same relaxation. So, and also if you just distinguish between odd and even, then they would all have one relaxation rate. Yeah. So by splitting them up, you are able to turn this into 3 parameters. Yeah. But you can, without doing asymptotic analysis, you can predict that you need 5. Yeah. So you have only 3. You need 5. So there is. So what way is there to solve it? So there is one glimmer of hope, namely by sheer coincidence, several of them could have the same root. Yeah. So, and in order to know this, you have to do the asymptotic analysis. Yeah. So, okay, I agreed with my because, I mean, from a theoretical point of view, it should not work. 20 years of research has resulted in nothing. And, okay, and then I agreed with then I told my PhD student, okay, let's try to actually prove that they are not the same, and then we can, rest this in peace, right? So now you have to do the expansion. Okay, so now there is an important simplification. If you do the asymptotic expansion up to, the leading order error, yeah, you get all these nonlinear terms in it. So your equation rises to, I think the first time I did this was 17 pages in Mathematica. Now comes the following. First thing is, these rates, they affect only the diffusion part, not the advection part. Yeah. So anyway, you're not able to do anything with advection in this place. So but the advection would blow up your result. So what you're going to do is let's completely forget about advection and linearize everything so that we only look at diffusion. Yeah, so that we actually have a chance to get the thing small enough, means still growing exponentially with the order, right? So that we get it small enough that actually computer algebra is able to solve the system. Yeah, I mean, you can try it by hand if you like. Yeah, I mean, it was so, which means we are actually no longer doing the complete asymptotic analysis, but we just do the Taylor expansion of the moment. Because why do we do asymptotic analysis and not just Taylor expansion? Yeah, recently Laura de Lorenz has asked me this because they are using linear systems. So why don't, I mean, actually everything works with Taylor expansion. Why do you use asymptotic expansion? Use asymptotic expansion because the system is non-linear. This is why we use asymptotic expansion. Then we have to separate things out which are of higher order because they are multiplied, so often by things that are higher order. So if we multiply two things of second order, then this thing is first order. You don't see this from Taylor expansion alone. You have to also expand you also have to do an asymptotic expansion. Everything is linear. You don't need asymptotic expansion. You just use Taylor expansion. So now you linearize your equation, and then Taylor expansion is enough. And by linearizing, you have to now rewrite your cumulants in terms of moments, and this leads to this kind of basically, so they would, this leads to a certain way of orthogonalization, like if you orthogonalize Hermite polynomial. So what we are doing here would be true also for Hermite polynomials, right? Because when you linearize cumulants, you end up with Hermite polynomials. Okay, so you see they have not completely, so I also wrote here the velocity part. So this still is not okay. That's not yet linearized so completely because there's still velocity here. Yeah. I mean, sorry. There's velocity square here. Yeah, but I linearized out the transformation so that it is actually in moments. Yeah, so I mean, one important thing here, and this is a little bit different from, okay, we are running a little late today, but maybe I still say this. So I have a little bit my own style in doing things. Maybe you have discovered this too, because what you could always do is to say asymptotic or Taylor expansion gives us the actual equations. Yeah, that is what we solved. So we implemented the way we expanded it. Yeah, my approach is a little bit different. Yeah, so I'm not, just because I don't get to these higher orders, I'm not ignoring these higher orders, right? So I'm using cumulants, and then for the analysis, I do the simplification. Now you could say, so we only know about the simplification, not for the full thing. So in principle, you could say, forget about cumulants. The derivation is for Hermite polynomials. Yeah, but we know that Hermite polynomials is just the approximation here of. Yeah. Something very important has to be going on. Getting so many messages. Okay, so that's the what you observe here. If you do this is basically you get these other terms here. So you have in this first order moments, now you have this B together with this second order moments, because the non-equilibrium, yeah, the collision term of the second order moments. Reason being, of course, we put them into their equilibrium artificially, right? So recursive equation for a collision. So we put them into here, and now we get what we've already learned. So we don't do an asymptotic expansion. We just evaluate this at a certain order here, and we see, okay, this gives us the continuity equation, and this here gives us the Navier-Stokes equation if we truncate at delta t squared. Now comes the actual linearized leading order. So we only look at the leading order of the momentum equation. Yeah. So we evaluate this, moment transformation of the Taylor expansion at alpha is equal to 1, beta and gamma equal to 0. This means we look at the x component because of isotropy, and because we choose everything isotropic. This will also be true for the other three directions too. And we do this to high enough order. Yeah. So this gives us a very long equation. This is why we need computer algebra to do this. So inside this equation, there will be showing up several time derivatives. Yeah, so this is the way how we get later to how many different terms we have. Yeah, so we'll have time derivatives and we have spatial derivatives. Yeah, and wherever we have a time derivative, this is our Navier-Stokes equation. Yeah, so maybe you don't recognize it as a Navier-Stokes equation, but if you put everything into here, it will drop out the Navier-Stokes equation. So whenever we have a time derivative of a velocity, we replace it with this. Also, if there are several derivatives chained on each other. Yeah. So the reason is we want to get rid of all the time derivatives because we want to compress all our error terms onto each few terms as possible. Yeah. Yeah. So another way that we use for elimination is we use kind of first the assumption of incompressibility, but as you have seen here, actually we have incompressibility to at least first order. Yeah, so we can push this. You can push this upward. So what we are doing is we have this first order derivative of the first moment, which is velocity. Yeah, we replace this using divergence. Yeah, and with this thing here. Again, the reason is we want to minimize the number of different terms that we have. Yeah, so and then we end up with these 5 terms. Yeah, and you can by simple isotropy reasoning, you can determine that there would be 5 terms, right? That you have these derivatives here, that you have this derivative, this sum of derivative by isotropy. They need to be the same. They need to have the same prefactor. These need to have the same prefactor, and then we have this. So I don't need to do the expansion to say that these terms here have to show up. Yeah, it's basically all the possibilities that have one x and an even number of the other directions. Yeah. So, because for isotropy reasons, the other directions, they cannot distinguish their chirality. So they need to be, always need to come in even order. Yeah. Whereas because it's the x Navier-Stokes equation, here x needs to come in distinguish its chirality, so it has to come in odd order. Yeah. So then you see. So here. Yeah, so for example, this here, because v is the velocity direction in y, if you combine it with a derivative in y, it's again even, right? And here is x is odd. Yeah. So now you can simply enumerate all these terms that have this property and all the ones that you can turn onto each other by rotating, and then you see how many terms there are. Yeah, and then it's very, very easy. So you need only 5 minutes to determine, you don't need any calculation, you need only 5 minutes to determine that there will be 5 terms, right? So, and you have 3 parameters to turn the prefactors of these things to 0. And this is what I wanted to show. And when I saw this, I realized the following, that by modifying because this depends on the equilibrium of this first order moment. So the equilibrium of so there's a second derivative of the equilibrium. No, there's a third derivative, third spatial derivative of the equilibrium of the first order cumulants in this equation. So basically, if you put the first derivative of velocity in the equilibrium of the first order cumulants, you can tweak into more parameters, because you have 2 different kinds of first order moments. So then I said, okay, if we plug these derivatives in the same way, in the isotropic way, into these first order moments, then there will be showing up 2 more parameters, A and B, which are not relaxation parameters. That are these parameters that we got if we go further. So I simply say, from an isotropic point of view, I can put in these parameters here. So that you see this is x to second order, so I put x to second order and it's y to second order. So this is isotropic to put this here. Yeah. So and then I simply put. Okay, so I could have put these things in I could have defined A in a different way so that all of this gets into A. But this is the way somehow I defined this. So it doesn't matter. Then I put a letter in front of this. Okay. So, and now this letter that I put in front of this will simply turn up here. Now, we have 5 independent terms and we have 5 parameters. And now the objective is to find 5 parameters, these 5 parameters, such that all of them, all these prefactors would be 0 at the same time. So previously, if you have fewer parameters, you still be able to put 1 or 2 of them to 0, and then for your specific case, if in your specific case the other derivatives just turn out to be 0 by the way the flow is, because it is never said that you have this first order derivative here. Yeah, if you have a flow where this is 0 and this is 0, then you don't need to care about this, right? But now suppose you're in a general case where you cannot say what of these things are 0, so you only get rid of them if you make all the others go to 0, right? So now right, so this is what you have to do. So you have to put all of them to 0. So there is one so there is one caveat here. There is tau 1. Tau 1, I remind you, is directly proportional to viscosity. Mm-hmm. It's just with a factor of the speed of sound. Yeah. So, and this turns up to be in third order. Now, since we are usually dealing with high Reynolds number flows, what we said here, because we did not like the solution that comes, actually, if I don't do this, Mathematica gives me a kind of solution. One that you don't want to see. One with, many different options, so with plus, minus, so several solutions. Yeah, it's very complicated. Yeah, third order polynomial. Yeah, because, you're solving for a third order polynomial equation. Yeah. Now this is viscosity cubed. And we are usually dealing with very low viscosity. So for example, if our viscosity is one thing that we like to have, it's 10 by the power of minus 5. Then this thing here would be 10 by the power of minus 15. It doesn't matter. Yeah? So what we do, it would matter if we were dealing with very low Reynolds number flow, right? But this is what you should know. So we simply assume that this thing here disappears. So we put this to 0. And now we have these other equations. And then when we let Mathematica solve these equations, we get these results, which look funny, but on the other hand, is extraordinarily simple if you think about what they are doing. Yeah. So, one thing, I think it is probably on the next slide. Yeah. A few observations about these things. The original application of finding these magic parameters was in the TRT context. So up front, they made a few assumptions, namely that they distinguish relaxation rates only between odd and even moments. So this means all the third order cumulants would automatically have the same relaxation rate, right? So what we see is that our solution requires all of them to be different. Yeah? So this cannot be done with TRT. Another thing is that also all the even moments would have to have the same relaxation rate. So there is no distinction between the shear viscosity and the bulk viscosity. And this is, by the way, also a controversial thing, because you will find people out there claiming that the bulk viscosity and the shear viscosity have to have the same value. And I don't know how they come to this idea, because physically that's not true. Yeah? It's simply untrue. Yeah? But still people in the Lattice Boltzmann community claim this. And I think, so there's always people who are just pissed because somebody else found something, I guess. Some people say if you don't do this, you cannot do acoustics, but it's completely nonsense. The problem with bulk viscosity is that it is very difficult to measure and not in the real world. Yeah, and it's not it's not constant. Yeah, so bulk viscosity, for example, depends on whether your air is dirty or not. So what is in your air? For example, if you have fog, or if you have humidity, yeah, and in particular if you have humidity, you always have you always have some droplets, yeah, and these droplets, if there are pressure waves, yeah, so they influence these pressure waves. So bulk viscosity of air is vastly different. Yeah, it's a big range of behavior, but it's by no means is it necessarily the same as shear viscosity. Yeah, they can be orders of magnitude apart. Okay, having said this, if we look at our solution, then we see that these parameters A and B, if we assumed that tau 2 is equal to tau 1. So first of all, this is what some people, for, in my opinion, completely physically meaningless reasons seem to believe. And the second is, this is in TRT, this is necessarily the case, right? Now, if you plug this in here, you divide by 0. So you only get a solution for the case that tau 1 is not equal to tau 2, which means that the bulk viscosity has to be different from the shear viscosity, otherwise there is no such solution. For me, very, very fine, because first of all, you can use bulk viscosity to improve stability. That's the first point. And second is, even if you do acoustic, bulk viscosity is not shear viscosity. It's not the same value. They're orders of magnitude apart. Yeah. And it would be completely sufficient if you made one twice as large as the others. At least from the parameter point of view. Now, again, there is something else, and this is related to this guy here. What you observe is that the arrangement here is such that this can become negative. When tau 1 is too large. Very good news is, okay, I just said could be twice, so this is probably not right. It has at least to be 7 times as large. Yeah, more than 7 times as large, I would say. Yeah. Okay. Now correcting myself from this equation, obviously. Yeah. But 7 is less than 1 order of magnitude. Yeah. So bottom line with this is, it works only for sufficiently small viscosities, which we have assumed anyway previously. Okay. So this is how these things look like. They behave relatively similar to the magic parameters that have been found previously. The equations are a little bit more complicated, but they behave very similar in the sense that they all go to 0 when viscosity goes to. Okay, so when omega 1 goes to 2, these guys goes towards 0. Yeah. So that means that the third order cumulants get close to being conserved, but not quite. Yeah? That's their behavior, and one of them is an odd man out, if you will, and is going negative in this, so it has a singularity. So using this is decreasing stability, in fact. So because now, okay, so when we use regularization means we put the third order moment, the cumulants, to equilibrium. So whatever is building up there is washed out with time. So this makes it more stable. And now, because they become almost conserved, they may build up something and go unstable. And in order to prevent this, we introduced an ad hoc limiter on them, which I thought will remove this with something better. And now we are here 10 years on, and this is still the only thing that has ever worked. Okay, so this is, I mean, designing this costs 10 minutes. Okay, so what is this doing? If this, the third order cumulant is supposed to be small, right? So it's relatively high order. So if it's increasing to rise because of instability, what we do is we have this, we compare to a limit lambda 3. So if you see if this here, if this is small compared to lambda 3, so we'll end up with the actual parameter. Yeah. So if this now gets large compared to lambda 3, so this will disappear, and we end up with 1 minus omega 3 here, which will eliminate this omega, so it will go to 1. So basically, if the third order cumulant starts to explode, this automatically sets it to regularization. Yeah? And by putting, however, because these things here are small, the modification is also small, and because then they are multiplied with the first order term that we have, this actually remains to be first order convergence. So it does not change the order of convergence. Yeah? Yeah, everything else that I tried out changes the order of convergence, but this doesn't, yeah, because it's simply designed that way. Okay, test. So, much over time. Okay, very simple tests is there are several here. So this is very simple. We do we have a shear wave, and we measure the decay of this shear wave, and we use diffusive scaling, and then we look at the different methods. So Cum1, sorry for the name, but this is how it was written in the paper. This is the K15, the regularized version, and here we have two different optimized versions with a strong limiter and with a low limit, with a not so strong limiter. So what we observe, if viscosity is not very small, is we get kind of still second order behavior, right? But the error term is here 2 orders of magnitude smaller than what we, for example, had in BGK. Yeah. So the same is still kind of true for some smaller viscosity. So if we make the viscosity smaller and smaller, what we finally observe is that it goes towards looking like first order convergence. It's not strictly first order convergence because we still have this tau to the cube term that would eventually take over. You could also complain that being higher order means it is less accurate at very low resolution. That can happen if you have a higher order method, right? So, that's not completely atypical, yeah, but if you go further with, the resolution, it will finally win. Yeah. Now there is something that we have been talking about before when we looked at this. How does it depend on because we now looked at diffusive scaling, and now we have a little bit idea of using mass, or we look at mass scaling. Yeah. So how does it behave at a given resolution for different time steps? And as we have seen, the small time step is here. Yeah. As we have seen, using a smaller time step and combining this with regularization leads to larger errors. Yeah, so that we can observe here. In BGK, this is not the case, but in BGK, using smaller time step finally leads to getting unstable. And the reason here is that when you use a smaller time step, so the numerical viscosity that you adjust with omega 1, so you have to make omega 1 larger, right? So then you get out of the stability range. So what I like with the new method is that actually here the error, I mean, it's leveling out. Yeah, it's leveling out, but the error is getting smaller. Initially, at least, is getting smaller with smaller time step. What you like to have. Yeah, it's not like the regularized version that goes up with smaller time step. Right. So don't read the small print. Now, what we did the Taylor expansion, yeah, we get the linearized leading error in the Navier-Stokes equation. Now, what we could do is to just say, okay, what is BGK, what is regularization, and what is optimized? Put the values in here and see what our 5 errors terms do, right? So, and of course, the optimized version, because we got rid of this tau 3 term, yeah, we ignored this, so in actuality it's still here, and we have this kind of error here. So, I mean, the true first order methods would not have these things. Yeah? They would then disappear. So, here, the BGK, so which I put in orange, this is kind of, so we also have this term of third order, which is, I guess, you can forget about this, yeah? So now, there is this error term, but this error term is kind of well behaved, so it all gets smaller, so because you see, this is delta x squared, yeah? So it's related to delta x squared, yeah? But nothing, okay, only here some time, but the time is also well behaved. What happens in regularization? And what is the problem? The problem is in this. And I mean, I have to remind you that all we know from asymptotic analysis is that we got convergence only in diffusive scaling, right? So, and also, this is kind of important. What we were looking at right here is keeping the resolution constant and making the time step smaller. Yeah. So there is no mathematical reason why we should have convergence in this case. Yeah, you're numerically not allowed to keep one smallness parameter the same and make the other one smaller and assume something gets better. Yeah, that in principle, this is wrongdoing. Yeah, so, but at least what you would hope, as in BGK, that it would remain the same. That the error would not get, I mean, you could always say, okay, this is increasing round-off errors, yeah, but this has nothing to do with round-off errors. Yeah, you increase the precision, it will still behave that way, right? So the problem being here is, and you see it clearly from the asymptotic, from this Taylor expansion here, yeah. If you leave the grid spacing the same, so delta x even by power 4 is a constant, and you make the time step smaller, then this is going up. Yeah? So this is the explanation why regularization loses with smaller time steps. Yeah, so you simply see it from the equation, right? So and everything that is turned here in red has this property. Yeah? Interestingly, some of them are positive and some of them are negative, which means some of them are stabilizing and others are unstabilizing. Okay, so the one application that we have shown this with, and that was also kind of a little bit of motivation, so it looks like a bullet, yeah. It's just the grid refinement around this sphere. So we'll put how many, so there are 3 levels, no, there must be more than 3 levels. So few levels. And, all right, so okay, no, it's not 3 levels. It's three different resolutions, which again, we have divided into more refinement levels. Right, and then we look at the track curve. So now what you need to know, if you're not aware, is that there is this that the track the Widerstandsbeiwert, the track coefficient in CD, yeah, of a sphere behaves like this. So if there's very low Reynolds number, there's this 1 over R behavior, yeah, and then it's going into an almost, then it goes into a plateau that spans 2 to 3 orders of magnitude, where the coefficient is the same, independent of the Reynolds number, and then suddenly this thing drops off by 80%. Yeah, so there is a very sudden point in Reynolds number. So if suddenly your ball is flying faster, the track coefficient drops suddenly by 80%. Right? And so previously we had very big difficulties to see this in the simulation. And here you see with the coarse simulation, you see it, but a little bit delayed. And with the finer ones, you get closer to actually see this drop pretty beautifully in the simulation. And the way this actually happens is, now you look at two different simulations of this sphere at 2 different Reynolds numbers, and you see that the behavior of the flow is different. You could almost guess, I know this is something that I'm not allowed to say, but you could almost guess that the vortices get proportionally smaller with the Reynolds number going larger. Yeah, so, but otherwise the wake looks pretty similar. Yeah, and the thing you have to look for actually is the detachment point of this turbulent wake, and this is here roughly of the order of 1 degree before in front of the pole of the sphere is the detachment point, and this remains in this place over several orders of magnitude in Reynolds number. Yeah? Now, if we increase further, so this is still, so it's still the same here. So this is still the same detachment point. Now, when you come to an yet increased Reynolds number, what suddenly happens is that the detachment point goes into the shadow of the sphere. And once it is, this is like a pencil dropping over. Yeah. Mm-hmm. Once it has been turned over this point, the flow behavior here completely changes. Now, what is actually happening here from the resistance point of view is that no matter how much dissipation goes on in the wake, Yeah, what the flow sees is this. So the flow here sees an extended sphere. Yeah, this is extended by its wake, if you will. Yeah, and once this goes behind, so this detachment point goes behind, so the entire wake is going into the shadow of the sphere. Yeah, so all of this resistance that the wake originally caused is now shielded by the sphere itself, and therefore the resistance has dropped drastically and very suddenly. Okay, so there is a few pictures from Q criterion and the pressure on the surface. I think we have taken now enough time that we actually come to this end. Yeah, so so there's a few papers that have been used here, almost 10 years old, and I hope this is still the right address that you can use if you want to get involved with virtual fluids, in which this is of course implemented now. Okay, so I'll go to turn off the recording, and then we can have our private discussion. Thank you for listening.